What?
Nothing. I'm supposed to treat you. And then we'll be live streaming now.
Please check the main app, which is it's on face track.
Okay.
How's that looking? He's on auto. Sorry.
Hold on, sorry. I'm just trying to finalize our Watch Now page so I can put the YouTube live link. Is anyone going to even see this YouTube live page?
What do you mean? As in what you've put on that?
Yeah, like right now as we're live. Is anyone going to see it?
I know Kim's watching on that if she's going to watch.
Okay.
We can also say, you know, signups are closed. But if you want to share this with any of your friends, feel free. Here's the link to the live thing.
Stream. Flipping hell. Stream. No. Do it live, as Henry says. We'll do it live.
That's who's the guy who is that Bull? Not Bull.
Turn down this light.
Which one? Henny's one. You can if you want. If that's what's causing the problem.
Yeah, he's still peaking.
What does that mean?
Like your highlight is too high. And I've tried to adjust things.
I don't know what that means.
As in the white parts of you are so white, they're off the spectrum. So it kind of, you've got no actual detail there.
I've got shiny bits.
Yeah.
A lot.
How's it looking now? Yes. That's good.
To do it live.
We'll do it live, Henny. We'll do it live.
It's a bit of a weird thumbnail.
It's not a thumbnail. It was, it was the actual video. Watch live. It's because it's live right now on the website.
I don't know.
Yeah, I just want to. Can someone just listen to the audio on? I don't. Is that thing on manual focus? Because the focus is terrible on this thing.
I don't know if maybe we're too close. Because it does that when you're too close.
Not the 85. No, but that's far enough that it should just be fine. Yeah. For those that are tuning in, we're getting ready for you guys.
Have you gone live?
Well, on our website, it's live.
We'll do it live.
How's it looking on?
He's looking good.
Okay. I'm gonna just start the video in the meantime. Henny, could you mute audio on your end? to everyone. Thanks for joining us on this wonderful Learning Space Tuition webinar, where we'll be covering Euclidean geometry, focusing on circle theorems. We really want to thank you guys for forming part of this, and I want to tell you guys we still have a few minutes before the webinar actually starts. Please send your guys, friends, the link to join us. Let's try and get this movement going. We want to get as many people on this webinar as possible, so we can all make maths super easy and all pass maths and do really well. Today we're going to do some really awesome stuff. We're going to meet a phenomenal educator, the Heinrich Cox, who's going to be our main presenter for the day. Introduce the concepts of circle geometry, make them super easy for you guys. He's got a secret guest. I'm not going to, but trust me, guest. Maths is going to be like so easy for you. You'll never feel ever again. And what I'd like to always again encourage you guys is to really make you guys in chat. Please note, as the video has been saying, engage in the Q&A section, not the chat section. So you've got a question, go into the question. There's a question that you wanted to ask is already there. We've got a free upvote. Simply go to that question, click the thumbs up, and it'll sort of tell us and our moderators that this is a question that really needs to be answered. And if we can answer the question in the chat, we will. Otherwise, we'll leave it for our brilliant mathematician, Mr. Heinrich Cox, to address at the end of the session. Again, because this is a very interactive session, we're going to have multiple formats of how you can engage with us. First of all, we're going to introduce a poll. So a poll is simply where questions come up on your screen. You get to give us an answer, yes, no, multiple choice. And we basically want to see how well you guys are able to engage with us in this webinar. And we're going to have several polls. We're going to start with one very shortly. And then I want you guys to just sort of answer as best as you possibly can in that poll. So I'm going to ask our technical team to get the poll up, and then we will see what answers you guys pop up for us. Okay. Introductory poll up, which again, it's asking what grade are you in, which province are you from. So if you guys could please answer those two questions, and then the last question is, how do you find this topic in terms of how hard is it for you, how easy is it for you? So please go ahead. Thank you so much. I see all the answers are coming through already. This is fantastic. Okay, pretty easy, pretty simple. So we're going to keep throwing these polls at you throughout the webinar, and that's how you're going to engage with us in this webinar in terms of giving us answers back. Fantastic, guys. At the end, we do have some super awesome giveaways. You might have seen it as the webinar was leading to its opening, where please follow us on our Instagram, follow us on YouTube, all our social media platforms, Facebook. And at the very end, we're going to be selecting one person from each social media platform, one person from Instagram, one person from Facebook, person from YouTube, who's going to have a one-on-one private lesson with Mr. Heinrich Cox, which again, if I was in high school, I'd be super jealous for that opportunity. So please go ahead, follow us on social media, follow us on those platforms, and keep going and checking regularly for new updates, for new videos and new awesome ways. So at this point, I'd love to introduce our for the day, Mr. Heinrich Cox. Mr. Cox, how are you doing?
I'm doing very well, thank you. And thank you so much, Ernest, for that lovely introduction. I really hope that everybody is going to find this to be such a useful and hopefully a pivotal section for you going forward. So that rather than, I was looking at the poll here, that this is a section that many of you find really difficult. And we're hoping that today, after this poll, you're going to have some more tools to be able to approach this section and maybe even start to enjoy it. So I'm really excited to get going. And I think we should do just that. Right. So, as discussed today, we are talking about Euclidean geometry, right? So as you expected, right? And to introduce this topic, I want to tell you that Euclidean geometry is a lot like learning to drive a car, right? So when you learn to drive a car, you've got to learn a few things, right? So the first thing is you've got to learn the names of the controls. So you've got to know this is a steering wheel, these are the brakes, this is the accelerator, here's the clutch, and here's the gear lever and all those sort of things, right? So you first have to know those basics. After that, you have to learn how these controls work together, right? So for example, if you want to change the gear, you first have to depress the clutch. If you want to turn, you first have to slow down and then turn the steering wheel. And then after that, perhaps accelerate out of the corner, right? So these things work together in particular ways. And then once you know how these things work together, you've got to go out and you've got to go practice your maneuvers, right? So you'll do taking off, coming to a stop without stalling, maybe parking, all these sorts of things. And then after that, you're ready to go out and drive on the real road without being a danger to yourself and others, right? So how does this apply to Euclidean geometry? Well, the first step is to know the names of the things in front of you, right? So I'm going to call these things the elements. And what I'm talking about is things like tangents, radii, center, words like segment, chord. What do these things mean, right? So we need to be able to know what this terminology means and what it refers to. Then we have to figure out how these things work together, right? So a theorem tends to combine some elements in some sort of logical way. So the tan-chord theorem, for example, will include a tangent, a chord, and an angle in the opposite segment, for example, right? So you first then learn how these things work together with the theorems, and then you're not going to go straight out onto the road, right? So you're first going to practice some of these individual theorems. So this is where, if you have a textbook, it's a good idea to go through the exercises before you get to the revision exercise at the end, or whatever you have that's been provided to you by your educator, or if you are privileged enough to perhaps have some extra help from a session, you can then some exercises that's going to help you build up to the final thing rather than throwing you in the deep end at the very end, right? And then the last thing is to go out and drive, right? So that's when you do your past papers, the complex riders, the things where you look at it and you're like, whoa, what's going on here? There's a lot of stuff to unpack, right? So let us then start with this in mind, right? So the first thing is, it's going to feel a bit basic, but we're going to pick up pace, right? So the first thing is the circle anatomy, right? So when we think about the circumference or the circle itself, it's blue, right? Center of the circle, radius, line from the center to the circumference. Diameter is a line that goes from one side to the other side that passes through the center. And then a chord goes from one side to the circle to the other side of the circle. Doesn't necessarily center, right? And then a secant is a line that's going to intersect the circle twice, but it just continues as much as it wants to, right? So those are basics. Let's make it a bit harder, right? So concyclic is a term that means together on the circle, right? So concyclic, if points are concyclic, then all of those points fall on the same circle. Now, a cyclic quadrilateral is basically a quadrilateral where the four vertices, those four places where sides join, are concyclic, right? And then opposite interior angles is what you see there in the yellow, right? So opposite interior angles would look something like that. And then an opposite exterior angle is basically if you just extend one side of the quadrilateral, right, then you end up with an opposite exterior angle. So just be very careful. Sometimes you might have something like that, like an angle that looks like that, and then you've got something like that. Now, that's not an opposite exterior angle because it wasn't formed by extending one of these chords that actually form part of the cyclic quadrilateral. So just be careful of that misconception, right? So here's another example of an opposite exterior angle. And then there's this concept of a tangent, right? So the tangent is a line that's going to touch the place, right? So then into this. So when you have a chord, the chord is going to divide into, right? So the minor segment is the smaller of those two segments, for instance here indicated in pink, and the major segment is going to be the larger of those segments indicated here in green, right? Then the minor arc is basically if we go from the start to the end of the chord along the edge of the circle, and that's going to be the shortest route, whereas the major arc then is what you get if you go the long way around. Okay, so let's look here at this angle ACB, right? So angle ACB here the terminology we use is to say that chord AB subtends ACB, right? So if you follow the two chords from C to the points A and B, right, then you'll see that that AB is what you get to, right? So that's a visual there to show you what it means when we say AB subtends this angle ACB. Now, not only can chords subtend angles, it is also true that arcs can subtend angles, right? So this arc here, AB, can also be said to subtend this angle ACB, right? And then it's possible for a chord or for an arc to subtend more than one angle. So here you can see that this angle ADB is also being subtended by the chord AB. And that's when we use this terminology, angles in the same segment. Because if you look at that segment that is created by AB, any angle that is in that segment, right, is also going to be subtended by AB. So if I put another angle there, for example, with my brilliant handwriting, then you can see that that angle there as well is being subtended by AB. It is also an angle that is in that same segment. Right. So this is where we get to meet the person who may help you going forward with your Euclidean geometry. And that person is going to be Dr. Cape Town. Okay, so Dr. Cape Town, as silly as it sounds, is a bit of a mnemonic device, if I can pronounce that correctly, that helps us to find a starting point by which we can actually approach these riders. So what happens with a lot of students is you get to the exam and you've got this diagram in front of you. And this diagram is very, very complicated, right? And it's not so easy to know where to start. Now, when we apply theorems, the way in which we do it is we identify which elements are there, right? And whether the necessary elements are there in order for you to make some further, not assumptions, but to know that something else must be there as a result. Okay, so this is just an explicit way to do what you already do implicitly. Right, so what does this stand for? So the D is going to stand for diameters, right? So this is your starting point. So you look at your diagram and you identify whether you have any diameters. If you do have a diameter, then you know that the diameter is going to subtend a 90-degree angle. Or for example, you will know that the diameter, as with a radius, is going to be perpendicular to a tangent. Next up is then to look for radii. So for radii, one of the most important things you can do is to always make sure that you mark the radii in the same circles as being equal in length, because this is often going to lead to isosceles triangles, which we know have equal angles opposite the equal sides, right? For the radii, you also want to see whether there's a line from the center that's, for example, perpendicular to a chord, or that bisects the chord, or that sort of thing. Next up is then to look for a center, because we know that the angle at the center is going to be twice the side of the angle subtended by the circumference, by the same thing. Then look for cyclic quadrilaterals, right? So here, it doesn't necessarily have to be a cyclic quadrilateral. You can also just have 4 concyclic points, which then allows you to maybe use the angles in the same segment theorem. And then the little known, most ignored theorem that most people forget is that when you have chords that are equal, they subtend angles that are equal. Right, so our Dr. Cape Town has 3 C's, center, cyclic quadrilaterals, and chords that are equal. And then the P is going to be for parallel lines, right? So we know about alternate, corresponding, and co-interior parallel lines. And then finally, the T is for tangents. We've got to look for tangents and then apply the theorems that pertain to tangents, right? So if you've got your rider in front of you, what I recommend you do is you first read all the information, read the questions, and then apply Dr. Cape Town, right? Now, when you apply Dr. Cape Town, by the time you are done, hopefully you would have extracted all the information that you possibly could from that rider. But you've got to make sure that you've always got your toolbox with you. Right, so the toolbox are those things that we sometimes forget that we're not explicitly looking for, but that we can use each and every time that it pops up. So for the toolbox, we're looking for VIP tips. Okay, so what are these VIP tips, right? So what you've always got to have in your back pocket is the idea that vertically opposite angles are equal, right? So as soon as you find an angle and you see it's got a vertically opposite angle, you want to mark them as being equal. The I is for isosceles triangles, right? So for isosceles triangles, we know that the angles opposite the equal sides are going to be equal, or that if you've got equal angles, that you must also have equal sides that are opposite those. The P is going to be for a point. So this we don't use that much, but frequently you have 1 or 2 or 3 angles around the point, right? And then you can use the fact that they all to 360 degrees to possibly find anything else, right? Then, very importantly, always the third angle triangle, right? So sometimes we find an angle and we don't realize that we've actually found the second angle in a triangle, which means that we're able to go find the third angle in the triangle by virtue of the fact that the 3 angles in a triangle always add up to 180 degrees. And then the other P is going to be for Pythagoras, right? So Pythagoras we don't always use in Euclidean geometry, but as soon as we have 90-degree triangles, we know that it is a tool that is in our toolbox that we've got to be ready to use, but it's often more useful when we're actually interested in the length of sides and not so much the size of angles. So use your judgment on that one. And then S is going to be for straight lines. We know that the angles on a straight line are going to be equal to 180 degrees, i.e. they are supplementary. Okay, so now you've got a method to approach. You've got that Dr. Cape Town, you can use all your theorems, and you've always got your toolbox in your back pocket that you're use every time find an angle and you see any of these things are relevant, right? So then the next thing is to just communicate to you some really important principles that are going to make your life easier when it comes to Euclidean geometry. Okay, so the first principle is this. The diagram is your guide to writing correct answers, right? So you analyze this diagram, you apply Dr. Cape Town, you do your things, and then you go to the questions. Now, you are going to refer to your diagram for each of those questions that you're trying to answer. So your diagram needs to tell you the story as clearly as possible. So it's very important that your annotations are going to be neat and tidy. And this one I know is controversial, but I actually recommend that you make your annotations erasable, which means either using it in an erasable pen, there are such color-coded erasable pens, or to use a pencil, right? So I know that it's nice to use highlighters and all that sort of thing, but sometimes what happens when you use something like a highlighter to annotate your diagram is that you get what I call tunnel vision, right? You can only see that which you highlighted. And if it wasn't the correct thing, it's going to prevent you from possibly seeing something else that you didn't highlight, okay? And then the other thing is sometimes you work through the diagram and you just don't see it. You're not finding the thing. And then when you look at your diagram, you take a step back and you look at it and you're like, this is a mess. This is a complete and utter mess. And then at that time, your diagram is no longer useful to you. It's actually a handicap when it comes to answering the questions correctly. So at that point, when you've made a mess, you really want to be able to tidy up. And that's when it's going to be fantastic to be able to erase. So I do recommend that you use either erasable pens or that you use a pencil in order to annotate on your diagram. Then the next thing, and this is for me the golden rule when it comes to Euclidean geometry, you prove. Okay, so often we're asked to prove or to show that something is, for example, a pair of parallel lines, or to show that something is a cyclic quadrilateral, right? Once you have proven that parallel lines, all the theorems that pertain to parallel lines can now be used. So as soon as you show you have parallel lines, you want to now go back to your diagram and look, are there alternate angles? Are there co-interior angles, etc.? If you prove that something is a cyclic quadrilateral, in your diagram, there isn't going to be a circle, right? But you still have to be able to then go and apply the to that well, cyclic quadrilateral that you've proven that actually doesn't have a circle around it. Note, I don't recommend that you actually go and try to draw a circle around the 4 points when it's proven to be a cyclic quadrilateral, because that tends to make more of a mess. And it's also really difficult to get it through the 4 things, and don't do it. Okay. And then the last principle I want to communicate to you is to relabel when it is appropriate to do so. So what do I mean by this? So you might start with this particular problem that I have here and use angles in the same segment and go and call this angle Y and this angle Y. And then you say this angle is X and this angle is X. Great. But then you might find out that this chord is in fact equal to this chord. And then you've got that theorem of, okay, equal angles subtend equal chords. But now you've got an issue. That means that the angle X is actually equal to the angle Y as well. Go inside, fine. Everywhere that I've got Y, I've got to go change it and make it X. Okay, so you've got to relabel your angles when it's. Now, I highly encourage you to use your diagram. So now, approach. You sit down, you read the questions, you apply Dr. Cape Town with your toolbox of in mind, and it's time to apply theorems. Or not, the theorems, let's have a look at theorems. So Dr. Cape Town starts with diameters, right? We angle subtended by diameter at the circumference. So you can see here that this line here is our diameter, and it subtends that angle there, right? So that angle is going to be a right angle. And the reason we use is angles in a semicircle. So basically, when you've got a diameter, the segments that it divides your circle into is a semicircle. So any angle within that semicircle is going to be a right angle. And that's why we use that terminology. Right, so what's super important is that you keep in mind that the right angle is often a second angle in the triangle, right? So you might have already been given an angle, right, like alpha, or it was 30 degrees or something like that, right? And then you go apply this theorem and you go draw that little right angle thing. But sometimes in our minds, we don't go, oh, this thing here means 90 degrees. And then we don't see it as the fact that actually we've got the numerical value of a second angle in the triangle. So whenever you do go and find that 90-degree angle, remember your box of, or your toolbox of things. And one of those things is the sum of angles in a triangle. And then you've got to go and say, actually, that third angle is going to be 180 minus 90 minus alpha, which will then give you 90 minus alpha. Okay, so then the converse is also true, right? If you've got an angle and it's subtended by a chord at the circumference of the circle, and that angle is 90 degrees, then the chord is a diameter, right? And for that, you can just say chord subtends 90-degree angle. So next up, let's look at the radii. So super important, as I said, is to always mark radii in the same circle, or rarely in identical circles, super rare, as being equal, because they will be equal in length. And then what often happens is that those equal radii are going to form an isosceles triangle. So remember, isosceles triangles are one of those things you always keep in your back pocket. As soon as I show that I have an isosceles triangle, I want to go think about the angles equal, the angles opposite the equal sides being equal, or the sides opposite the equal angles being equal. It's quite a tongue twister. Right, so we want to then show or conclude that those two angles opposite the equal sides are going to be, in fact, equal. Right, so then the theorem that we see most often with radii is that the line from the center of a circle perpendicular to a chord bisects the chord. So remember, we need to know our terminology. Bisects is just a fancy way of saying cut in half, right? So cut in half perfectly, such that the one side is the same length of the other side. Or if you bisect an angle, then the two angles that it creates are going to be equal.
Dissects are when you cut something into two pieces, but they're not necessarily equal. Right, so if you've got this, a line from the center that's perpendicular to the chord, then you can conclude that the chord is being bisected, right? So those two things are equal in length. And note that even though I've put this under radii, it doesn't have to necessarily be a radius. So often it is a radius, but it can also just be a line from the center, as I've indicated there. And that's then line from center perpendicular to chord, all right? Then if you have the line drawn from a center of a circle perpendicular to a chord that bisects the chord, right, then that is going to be perpendicular, right? So here you've got a line from the center. Now you've got the chord being bisected, and now you can conclude that it is in fact perpendicular to that line, right? And then the final one is basically if you've got a perpendicular bisector of a chord, then it's going to pass through the center of the circle. And again, it doesn't have to be a radius. Often it is, could also even be a diameter. And that's the perpendicular bisector of chord, right? So it might feel like I've run through this a little bit quickly, but I'll show you just now how we're going to bring all three of those theorems together in a lovely way. Okay, so here's a tip. Sometimes questions revolve around finding the lengths of line and not finding angles, right? And whenever perpendicular lines or right angled triangles exist, as we said in your toolbox, you are looking to use the theorem of Pythagoras, right? Now here, especially when we've got this theorem, you've got to be ready to construct a radius to complete the right angled triangle, especially when, as we said, you know the length of the radius. So what do I mean by that? Let's say, for example, they tell you that this radius is 10 units, right? And maybe they tell you that this line here is 5 units, right? If you want to go find the length of this line, for example, you can go draw in this radius, and because all radii are equal, this will also be 10 units. And then you can use Pythagoras in order to go find the length of that line. Okay, right. So this is how we bring it all together. Now, these three theorems are not really three separate things. Sure, they've got slightly different reasons and all that sort of thing, but I think of them as being three pieces of the same puzzle. And no, I'm not referring to these puzzle pieces down here. That is just the logo for Learning Space. But it's three pieces of the same puzzle, right? And basically, those pieces are a line from the center, something that's being perpendicular to the chord, so that particular line, and the bisection, the cutting in half of that chord. Right. So if you have a line from the center and it is perpendicular to the chord, as it is indicated in that diagram, you know that it bisects the chord, right? If you, for example, have a line from the center that bisects the chord, you know it's perpendicular to the chord, right? Or if you've got something that's perpendicular to a chord and it bisects the chord, then that's a line from the center, right? So basically, you've got three pieces of the puzzle. If two pieces are there, you can always conclude that the third must be true. Okay, right. So let's keep going here. And now we get to do our first exercise, right? So what I'm going to do is I'm going to give you 4 minutes to first look at this exercise and see whether you can apply Dr. Cape Town, right? So apply Dr. Cape Town as well as you can, right? And then we're going to launch a poll where you are then able to answer one of the questions. And one of those questions will be, find the length of DB, right? So we want to find the length of DB, use Dr. Cape Town, and at the end of that poll, we're just going to talk about where on earth all these green things came from and what they mean.
Measure the length.